So here, very quickly, we're going to work on just a few problems from chapter 13. I wanted to do problem 27, where we are looking at an intravenous feeding situation. And what we're told is that our patient, who I've drawn here in the bed, see, it's patient in the bed, it's not a very good cartoon, has a intravenous pole that's been raised. And the reason that we're going to raise the intravenous pole is that we need the fluid pressure at the bottom of the intravenous tube to exceed a certain pressure that is in the patient's arm. So in order for the fluid to flow from the intravenous bag into the patient, we're told that the pressure in the intravenous fluid needs to be greater than 1,400 newtons per square meter above atmospheric pressure. So the pressure in the person's arm is the atmospheric pressure plus 1,400 newtons per square meter. Now, the pressure in the fluid at this height where the patient is located, at the height here, is going to be equal to the atmospheric pressure plus rho GH, because the intravenous bag is raised a height h above the location of the patient's arm. So the fact that the intravenous bag has this height differential leads to this added pressure from the weight of the fluid. And then as a minimum condition, we're going to set these two quantities equal. So if I set these two quantities equal, then I would see that the pressure from the atmosphere plus 1,400 has got to be equal to the pressure of the atmosphere plus rho GH. I'm told the density of the liquid, that's my rho, and my G is my 9.8 number. So the atmospheric pressures cancel out, and the height that I need to raise this to would be 1,400 divided by rho H, which is 1,400 divided by 1050 times 9.8 is my, rho G here. So the 9.8 is my G value, and when I compute those numbers, I get something like 0.14. So I need to have the pole be at least 14 centimeters above the patient's arm location. It would be better to be higher than that, so the drug would flow freely through the intravenous solution into the patient's arm. So let us also maybe do problem 53. So problem 53 has to do with buoyancy. And this is a ranking problem, and you'll notice that in a number of the ranking problems in the books, you will see that sometimes the values are equal, even though they tell you to rank them. In this particular problem, they say that you have, 4 different vats here filled with 4 different liquids, and you have the same piece of wood, and you put the piece of wood in there, and the density of the wood is 900 kilograms per cubic meter, is the density of the wood. And we're going to put this in water, and if you look up in the front of this chapter, the density of water is 1,000 kilograms per cubic meter. We're going to put it in olive oil, which has a density, according to the book, of 800 kilograms per cubic meter. We're going to put it in alcohol, which is even less dense, 790 kilograms per cubic meter. And we're going to put it in mercury, which has a very high density of 13,600 kilograms per cubic meter. So the first question is, if you put this block of wood down in here, what's going to happen to it? Well, in both the water and the mercury, the wood's going to float, because the density of the wood is less than the density of the fluid. And if that's the case, the wood is simply going to float up on the top. Now, in the floating situation, there's a force of buoyancy pushing up, and there's the weight of the object pulling down. And those two things are going to be equal to each other. And so the force of buoyancy of the of the water and the mercury are going to be the same. Because the wood block is just going to displace just enough water density so that it floats. Now, if I stick it down in the oil, and the olive oil and the alcohol are both less dense than the wood, so these are going to sink. So in these cases, the wood would sink to the bottom. But if I held it up here, then it might not sink entirely to the bottom. So I'm going to assume that what they mean is that it hasn't sunk all the way to the bottom. It's not sitting on the bottom. So while it's in the fluid, drifting down towards the bottom, we can see that the whole piece of wood would submerge. And since the entire piece of wood would submerge, the entire volume of the wood would be beneath the surface of the water. So in the sinking cases, so in the olive oil and the alcohol, the entire block is submerged. And then the force of buoyancy is going to be equal to the weight of the displaced fluid, which is the mass of the fluid times gravity, it's constant. So that's rho for the fluid times the volume times g. And in both the olive oil and the alcohol case, because the entire block is under the fluid level, the volumes are going to be the same. And so the one with greater density is going to have a greater force of buoyancy. And so since rho of the olive oil is greater than rho of the alcohol, we can see that the force of buoyancy of the olive oil is going to be greater than the force of buoyancy for the alcohol, and both of those are going to be less than the force of buoyancy of the water and the mercury, because in this case it's floating, and so the most upward force you're going to get is equal to the weight of the object. And in the second two cases, because it's submerging and it's sinking, you could have a different force of buoyancy. The more dense the fluid is, the more force of buoyancy you would have upward.